Thank you everyone for coming for the seminar. Our seminar speaker is Dr. Teresa Barnes today. She's actually interviewing for a faculty position in mechanical engineering, the materials position in mechanical engineering. Dr. Barnes is actually right now a scientist at NREL, and I think she knows many people here in the audience and has also worked with some people here in past as well. She got her bachelor's degree in chemical engineering from University of Maryland in College Park, and then a PhD also in chemical engineering from School of Mines. And then she ended up at NREL as a postdoc, and then she has been at NREL for quite a number of years now. So with this brief introduction, welcome to CSU, and I'll have Dr. Barnes will talk about her research.
Well, thank you guys for having me. This has been a really nice day up here. Let me know if you can't hear me in the back. I tend to get quiet when I get tired, so it's a wave or something. So I won't go through too much of my bio, other than that I am an informally trained materials scientist and solid-state physicist. Over the last 10 years at NREL, that's essentially what we do. And so that's where most of my expertise has been lately. I am an experimentalist to my core. We use simulations as needed, use them to help understand some of our processes, but generally if it won't potentially blow up or catch fire, we're less interested. I really like to get my hands into things and do things. My primary...
What is your pointer?
My primary area of interest is cadmium telluride solar cells, quite similar to what Sampath's group does. I think we work a little bit more on the fundamental materials science side of that in terms of the CadTel material properties itself. But we take a similar approach of using the device as a test platform for our materials and our improvements. I do a lot of work with hetero interfaces because in polycrystalline device stacks you have a lot of mixed materials coming together, and those can behave in pretty funky ways. We're getting into varied interface characterization in a pretty big way this year, processing science, and new materials development. So here's a little bit on things I've worked on in the past or am doing currently. A project on interface science and engineering, basically surface passivation to improve CAD telluride device efficiency, and a lot of fundamental characterization work on interface defects and that sort of thing. Another very fundamental project using molecular beam epitaxy that's approaching the Shapley-Queisser limit with CadTel to look at the fundamental limits of CadTel performance. How far can we push it in an absolutely perfect material? How great of a semiconductor could it be? So that we then know where our limits actually are for the polycrystalline commercial material. And then the project I'll talk more about today, which is this high temperature roll-to-roll CAD telluride superstrate devices using flexible glass. We just finished this up, and I'm going to talk about it a little more because working with flexible glass is inherently pretty cool. It's pretty neat to think of glass. You can wrap around a roller and you can bend and you can do all sorts of things with it. And it's an interesting thing to work on. Outside of CadTel, when we didn't have a lot of money for CadTel, we had to go do other things. So I worked on carbon nanotube and silver nanowire networks, doing a lot of nanoscale transport type things to make those into transparent contacts and understanding how they work. So I just put up a little picture of one of our flexible solar cells, along with the the atomic structure of CadTel lattice with the dopant in it, and then some of our long lifetime work that we've done by NVE. So I thought rather than diving into the depths of why this helps you do this, and a lot of CadTel point defect details, since there are maybe 4 people in here who care about that, maybe 5, this is an unusually large CadTel group. I thought we'd go a little bit more general and start to motivate this with why I'm into renewable energy and thin film photovoltaics specifically. And so this is a project out of NREL called the Renewable Electricity Future Study. And what they did was look at how much energy can we potentially put on the grid from renewable sources, accounting for the fact that wind and solar are intermittent, geothermal occurs where it occurs, biopower happens where you have stuff to burn, and those sorts of things. And what could that scenario look like in 2050? How much energy could we get from renewable sources? And the answer is a whole lot of it. We can get up to about 80% of total US electricity generation. And PV here isn't necessarily the dominant technology in this picture, but there's an awful lot of it in places where we have a lot of sun. And so PV is an area that's going to continue to grow. Now the issue with getting more PV on the grid is that you don't always need a lot of electricity while the sun's shining. And people only care about electricity if you have it when you want it. Nobody cares if you have power for lights in the middle of the day. And so what ends up happening a lot of the times, especially in the spring for reasons I'm not sure I totally understand, you get a lot of what's called curtailment. And what curtailment is, it means your PV is turning on and producing a lot of power, but you don't actually need it. And so you actually don't get any value from that electricity that you're producing because you've got to either turn that off or turn something else in order to accommodate it on the grid. And this is a very high solar penetration picture here with 25% solar on the grid. So it's a little bit extreme, but it's something to think about because when you do this, you effectively reduce the value of your PV that you put on the grid. And that means that even though PV is the cheapest energy source on the grid right now, because of curtailment, you actually need to make it even cheaper and even better. It works as it is right now, but in order to really increase penetration to the point where we're getting 80% power from renewables, this is going to be an issue. It also increases energy payback time because you're getting power out that you're not using. We'll talk a little bit more about that later. And there are a lot of ways to mitigate it. And one of these is actually better grid flexibility, so that's why you guys are doing some work in smart grids, why we at NREL do a lot. But one of the big needs is to make PV dispatchable, meaning you can have the power when you need it, instead of just when the sun is shining. And storage essentially enables higher renewable penetration, and that's why a lot of us who work in PV are also very interested in storage. It's because the more power you can store, the more PV you can put on the grid. That helps with decarbonization, and when it comes down to it, that's actually our goal. My sub-goal is to make, Cadmium Telluride PV take over the universe, but that doesn't actually matter if we're not decarbonizing and actually addressing climate change. Problem is storage is really expensive, so it doesn't make the PV cheaper right now, but addressing that problem helps us get to a lower carbon energy infrastructure. And dispatchable PV is really critical for worldwide development in places where they don't have reliable power now. If we can prevent them from putting in a coal-based grid and instead go to a renewable-based grid, that is fantastic for development, health and safety and all that other good stuff, and probably cheaper. But it has to work. Nobody's going to settle for power only part of the day. So considerations for actually implementing a PV technology when you're looking at either a new technology or scaling into an existing one is, the first one is efficiency. Does it work well enough to be worth using at any kind of scale? Nobody wants to adopt a 5% conversion technology. There's always some minimum threshold above which people want things to work. And then cost, is it competitive with our current energy costs? Technology doesn't have to be cost competitive from the get-go, but it has to have some potential. And the one that we talked a little bit about this morning that I don't particularly like, because I wish this wasn't such an issue with PV technology development, but it comes down to it. If a PV manufacturer is not making money, they're not going to keep making the PV. And you need to make it profitable. So you need to have a sustainable margin between your manufacturing cost and your selling price. And that's actually where a lot of the challenges in PV are right now. And then finally, reliability. How much power can I count on long term? How long is this technology going to last? Is it going to outlast my roof or not? And bankability. This is a big issue for utility grade systems. Can I get somebody to finance this project? Do they have that confidence in this technology to finance my project? The other issue is energy payback time. How many of you guys have heard a PV cell will never ever pay back the energy it took to make it? I know I've heard that.
I heard that.
And so I'm sure Sam has heard it 1,000 times. Actually, it turns out that's not generally true, and I'll talk about that in a bit. But this is important. You want to make sure you're going to get your energy back out that you put in, and then some, because otherwise, why bother? And then efficiency is on here a few more times, because it matters that much. You've got limitations on area. If you have a 5% cell, you're going to have to cover miles to power, even something fairly small. And nobody has that much space. The other issue is that all the other stuff that goes with the PV system, the balance of system, inverters, components, it's actually more expensive now than the PV itself. And so if you need a lot of that stuff because your cells stink, nobody's buying. And then reliability, really this matters. Perovskites are awesome, but we're not commercializing technology that we have to sprint to the glove box to bet. That's just well worth further research, but unlikely to get commercialized anytime soon. So this is just a different version of the standard NREL PV chart. I stole this one from Fraunhofer because nobody likes to look at the NREL one anymore. And I thought it's actually a little bit cleaner version comparing a monocrystalline silicon. These are typically been the best of the molecules. So this is going to be like a SunPower product. With a multi-crystalline silicon, here's a cell efficiency and then a module efficiency. This has dominated the market. This is probably what, Kurt, 95% of the market right now, multi-crystalline silicon, 90%, something like that?
No, I think you're close to 85%, with another 10% being mono.
Right. So, I mean, these two are really dominating most of the market. What you'll notice here is that very recently, cadmium telluride record cell efficiencies have not only eclipsed CIGS, which has been our traditional thin film PV competition, but also multi-crystalline silicon, both in terms of cell and then very close in module. And these numbers really, this number in particular hasn't moved in years. And CadTel, it's got legs, it's moving, the efficiency's climbing quickly. And nobody cares about morphosilicon so much anymore. But we're seeing some very, very big improvements here in technology. And then here's the other way to look at it with production module efficiency, where instead of looking at records, we're actually looking at what's coming off the line on a regular basis. Obviously going to be lower. So the monocrystalline silicon is going to be the highest, multicrystalline is lower. CIGS is down here, which is copper-indium gallium diselenide. And then cadmium telluride has historically been the lowest. But you'll notice this paper's from 2014. The data might be from 2014, but probably not all of it. And what's happened very recently is that CadTel module efficiency is now here. And so we've got a very different shaped curve for production modules and a much higher module efficiency. These guys are silicon guys, so they're a little biased to this paper. But a much higher efficiency than people really expected for solar's really been moving quickly. And they have asked for academic support to continue that movement. So one of the most compelling aspects of CAD telluride technology is the cost. And this is from that same paper from Verlinden on module price or cost versus cumulative production. And so here there's a bunch of different technology, expected learning curves for CIGS, and then actual prices at CadTel here. A bunch of silicon companies clustered up here. And what you can see is generally with the lowest cost, with the exception of maybe Jinko over here, CadTel tends to have, at pretty large production, the lowest module prices, which is very important. If you can have the best technology at the lowest price, there's no reason for you to buy something else. And when you have something like cadmium telluride that's relatively small percentage of the total market, that's actually important if you want to gain other people's market share. That makes a big difference. Now the big difference between CadTel and silicon is when you start to look at average module selling price, which is the red curve here, and production cost, which is the blue curve here. Anybody see a problem with these curves? Yeah. Any of you guys see it? Which one do you want on top? Okay? You can't sell below cost for that long before really bad things start to happen. And that's what's going on now in silicon. And I took the slide out that talks a little bit more about this. You know, is this economically sustainable? And CadTel is the only technology that consistently has the curves flip the way you want them, because the manufacturing cost is inherently so low in that technology. So we talk about energy balance. This is how much coal does it take to make my photovoltaics? And these are some slides Tim Gesser gave me a while ago. And you start to look at, essentially, when do I get the energy back from the coal plant I used to make my PV, in terms of PV on the grid? And you know, if your energy payback time is a year, you know, things look okay if you're making more PV, but it can start to get complicated pretty quickly. So here's kind of a mess of a slide, but if you imagine an energy payback time of 2 years and a production doubling time of 1 year, so you're ramping up pretty quickly, and it takes about 2 years to pay back, and every black square here is some cumulative amount of power you use from coal to build your PV. You're basically building coal plants to make PV, and a little bit of PV to make PV. But the net benefit of this is probably pretty small unless you either sell coal, sell power plants, or sell PV. Not really helping people a whole lot. Here you reduce the energy payback time to 1 year, and these are all kind of arbitrary units. This is kind of a cartoon illustration here. You got to build one coal plant to make some PV, and then you can build all the rest of your PV with more PV. Better, I guess. At least not net worse. And then let's say you cut your energy payback time down in half to 6 months. And then all of a sudden you start to get these blue squares where as you make more PV, you actually start to put some power on the grid. and actually add some power to the grid, and you start to get a net benefit. So there's got to be some relationship here you have to maintain between your energy payback time and your production doubling time. I'm not going to argue that this is exactly right, but this is kind of how the problem works. And so what are the energy payback times in these technologies? And this is data from Fraunhofer. First Solar has one that makes CadTel look even lower, so I thought I would take one that was ostensibly a little more neutral. But actually, I don't argue with their data. It looks pretty good, and it's not far off of this. So here you have monocrystalline silicon, where most of your power is going into making that wafer. Because it takes a huge amount of energy to make a silicon ingot, and then cut it all down, and do all that stuff. And then you've got some power to make your cell, and then you've got the rest from the essentially modules and laminates and that sort of stuff, mounting, and then your balance of system stuff here. And you're at almost 2 years to get the energy paid back out of this thing, even though the efficiency on these is, here it's probably too low. At 14.8%, they should be higher. But that's a long time. At a similar efficiency for multicrystalline silicon, because you don't have quite as much energy going into the silicon production, you're at a little over a year. Amorphous silicon, not that the stuff takes too much energy to produce, but the efficiency at 7% is just so low that you can make calculator solar panels forever without actually making enough to pay one back. Microcrystalline silicon, again, a little bit lower because it's a little less intensive than this and a little more efficient than amorphous. But CadTel, you see here, is pretty low, and most of it's in the other components other than the cell, the CadTel itself. And a lot of that comes from like the glass. It takes a lot of energy to make glass. And then SIGS is a little higher because it's a little more complicated to make, and then finally concentrating PP here. What you can see is CadTel is pretty close to that half a year time, which is where we wanted to get, to generally have a technology that's growing pretty quickly and going to pay back in energy pretty quickly. So another argument people like to have about cadmium telluride when they want to get work funded on kesterites or other similar materials is that there's not enough tellurium on Earth. Look at tellurium, it's down here in the rarest metals category. We talk about it with all these really rare elements, which actually aren't that rare. I mean, anybody here ever heard of a gold mine? Platinum? It's pretty close. And so you can actually think about it this way. If you look at a total crustal abundance, this is accurate. However, we don't mine by total crustal abundance, and this is where having a good mineral economist on your side can help you understand the fact, especially that the guy who started Primestar Solar, one of the other CadTel companies, had been a mining economist at Newmont Mining for a very long time. Because you look for enriched sources of whatever it is you're looking for. And here we see, okay, over the entire crust of the Earth, there is not a lot of tellurium. But it turns out here, in Chile, where there's a lot of copper and zinc mining, there actually is a lot. And they're getting it as a byproduct of other things in these different places. Usually as a byproduct, mostly of copper, but some zinc. And so the law of mineral economics is that when the price is right, they'll find more. I apologize if this is blurry. But essentially, when a material is pretty cheap and the demand's not that high, they'll look for it as a byproduct of something else, and we can do a better job of finding the tellurium slides we have and get more. Comes up a little bit, maybe they'll enhance recovery of some of those other things. And then maybe they'll start recycling, and then eventually, once the price gets high enough, somebody will build a tellurium mine. That's actually happened in China now. I don't think it's still in business, but it exists, it's possible. So that argument is also a little bit misplaced. And so looking at that and knowing that the tellurium price is going to have to go up a little in order to mine enough to get what we need, you have to start looking at what factors actually affect costs in PV. And this is a chart that our cost analysis people put together. And it's all actually skewed, kind of high compared to where costs actually are now. First Solar's costs are actually lower than this. But if you take a 2011 benchmark cost of 74 cents and a price of $1.07, so again, margins, this is good stuff, you could add up to 53 cents a watt if the tellurium price went up by a factor of 10. So this is potentially a very big jump, but so is this. So keep in mind that that's what could affect you to increase cost. You could also use less of it, so you could make a thinner semiconductor. If you didn't have quite as much CadTel, that's something that's very active here, and that has the potential to bring your cost down. You can also increase efficiency. If your cells work better, you don't need as many. This is also good. And now actually cell efficiency is higher than this. And so that could get you another 40 cents down. Finally, you can make your capital equipment cheaper. You can go with simpler processes. You can go with less expensive equipment, or maybe you bought so much the cost has come down. And with that, you can get your cost down to below 60 cents a watt. On the net, you're accounting for this increase in tellurium price. And so this is part of how they've continued to push prices down. And then it's kind of a final slide on how PV technology has evolved. And I guess Sampath can correct me on this if I get it wrong. But when I came into PV 15 years ago, we were told that there is this general concept of generation 1. This is the commercial silicon and polysilicon. This is the stuff that will come into the market first. And then the thin films will get better, and they will be cheaper, and they will then replace the silicon or take over that market. That hasn't happened. And then once thin films come in, these other things, nano and organic PV and all these crazy exceeding Shockley-Queisser limit PV things will come and take over the world with the lowest cost and the highest efficiency. And I think one thing to keep in mind is that it hasn't happened this way. We have to come up with a real different way to think of how PV technology is going to evolve. And some of that is not going to be displacing the dominant technology, but coming up with new applications, new markets for things that we make, and actually creating new applications for these things that we make. And on that note, one of the things we do is high efficiency, flexible cadmium telluride. And this is something that not a lot of people do, because cadmium telluride is what's called a super straight configuration. We talk about two general configurations of thin film solar. And one of them is a substrate, where you take any kind of substrate, either glass or metal or whatever, it could be opaque, and you build the cell first by putting, I'll use the SIG cell as the example, the metal back contact down, then the absorber, and then the transparent contact and window structure at the top. When you have what's called a super straight device, you have to start with something transparent, because you're starting from the end that you let the sun into. So you're going to start with your transparent contact and window layer, then put your absorber down, and then your back contact. And the challenge to making flexible CAD telluride is to find a flexible substrate that is also adequately transparent and is amenable to our 600-degree processing temperatures and very, very harsh environments. So you look at ideal properties for a CAD tel substrate. It has to be highly transparent. It has to be very dimensionally stable at high temperatures and chemically stable. We also want something that is what we call hermetic. We don't want it to let water in or out or any other funky stuff in the atmosphere. We want it to isolate if it can. CAD tel is actually very, very stable, but you save yourself a lot of reliability problems if your substrate just seals everything out for you. And then we want it flexible. And so what I'm showing here are some rules of what's typically used as a flexible, transparent substrate. And it's kind of orange for my taste. I prefer mine much more transparent. So the other thing to think about when you think about a flexible substrate is what actually matters. What are you going to do with this thing? Do you need it to be flexible so you can do roll-to-roll manufacturing, but after that it doesn't need to flex? Or do you need it to be flexible so that you can put it on a tent, or roll it around a pencil, or crumple it up in your pocket, or put it on a backpack? These all have very different mechanical requirements for a substrate and for the device. And so you have to kind of think through that as you're picking a substrate. And the other thing to keep in mind is, are you looking for something that's just flexible, or do you care more about weight? Are you going to put this in a soldier's pack? Or actually weight is the deal breaker. And then there are some different requirements. For a rooftop, you need it to last 30 years, but you don't really care how much it weighs within reason. For portable power, that specific power weight, that's going to dominate. And so here's a picture of actually a flexing CAD tel device that I'll probably show a couple times. And this is something we've been thinking about a lot as we make these. You can see that this substrate isn't as flexible as a plastic foil would be. Primarily that's because it's so small. When you take an 1.5 inch substrate over a 6-inch bend radius, it doesn't look that impressive. When you take a really big piece of glass over a 6-inch, or excuse me, a 3-inch bend radius, it actually looks pretty cool. Kind of looks like saran wrap, but it's glass. So we talk about lightweight, flexible substrates for CAD tel. If we could make something with the cost structure of cadmium telluride and the performance of something like even gallium arsenide, then we can start to talk about opening new markets, even at the current CAD tel efficiencies, because we could have something that was affordable. Can we open a new market because we have lower install costs, lower transportation? We can get this into remote areas. What can we do? And so this is a little bit on the literature background of what's out there. In Flex PV, before we started, there's some work from IMPA with 13% cells, and they actually went and integrated some modules. in Switzerland. But these are all made on that polymer substrate where their efficiency is really limited by that yellow-orange color when it's the current. They've also flipped the device. You can make an upside-down CadTel device, but historically with far lower performance than the way that we usually make it. And 11-12% for those is actually pretty good. And here's one of these on a metal foil. So there are a few people actively working on this to see if we can do really high throughput, really lightweight solar. And one of those potential customers for us is actually the military. And what DoD really cares about, and what we talk to them a lot about, is specific power, so watts per kilogram. They also care a little bit about aerial density, which is generally captured kind of in efficiency. You know, you don't have infinite space. And so what's important to think about in specific power is we've had people tell us that the TCO, the oxide coating weight, is what they think controls the specific power in a cell. And that's nuts. Because what really controls the cell weight is the other stuff, everything but the cell. In silicon, you're going to have something that's a little heavier because you have a wafer. So here's a line for about 3 kilograms a meter squared with a full package. But it's really your substrate, your packaging, all that other stuff around it. So if you're on a stainless foil, in order to be thick enough to get that foil to have the good mechanical integrity, you're inherently going to be kind of heavy. If you're on a 3.3 millimeter slab of glass, that's going to be really heavy. If you can go to this 100 micron thick flex glass, we're pretty sure we can get to 550 grams or 350 grams per meter squared of packaging, which would help us get to our specific power targets. And then finally, if you can move to an ultra-thin plastic, is going to be the lightest, and that would be fantastic. However, it's not compatible with our thermal requirements. So we can either re-engineer our process or come up with a way to divorce our cell manufacturing from our packaging requirements, and that's actually what we're working on right now. So the other thing that comes in with these portable devices, and this is from our cost people, without real hard numbers on a lot of things, to look at cost per watt versus efficiency over a certain range. For cadmium telluride, CIGS is going to be higher cost because there's more elements in it, it's harder to do. Multicrystalline silicon is going to be a little higher, crystalline silicon even higher still. And then when you're looking to move into portable power for either manpack applications or for space, the standard is triple junction gallium arsenide or single junction gallium arsenide. And the issue here is that the cost per watt is conservatively a couple $100 a watt. And that is just really expensive, especially compared to under $1. So you're selling to DoD and NASA, and you assume that money doesn't matter. And it turns out for some applications like space, that might be true. But as we're starting to fly more and more and more things into space, we might start to care. The other issue is if you're going to sell the Marine Corps 100 packs, they probably don't care if they cost this much. If they need to buy 500,000 of them, they don't need it to be this cheap, but it better be somewhere on the lower end of this graph. And that's something we've heard from them repeatedly, is that they want things that are potentially cost competitive. They don't need it at $1 per watt, but they aren't able to pay 100. So we need to bring that cost down. And to me, that's also something that's screaming for an entrepreneurial solution, as it has kind of a built-in sweet margin to it. So when we look at super straight materials, Corning came out with Willow Glass maybe, I don't know, 6-7 years ago. And this is a new material. So here they put Kapton tape around the edges of it so you can see it. This is what we call a technical glass. So it doesn't have any of the stuff in it that makes like the Tech 15 that you guys use look kind of green. It's from iron. It doesn't have any sodium in it. It doesn't have stuff that's going to diffuse out. So it is really, really clear. And they make it in a couple different thicknesses. We usually use about 100 micron thick. And so here what I'm showing is the transmittance of a couple different kinds of glass and the standard polyimide. This is the high transparency, really thin polyimide that people use. And you can see this has an absorption edge cutoff about 400 nanometers and a lot of features going out towards the red. If we look at soda lime glass, this is iron-containing soda lime glass, and so it's still got quite a lot of optical absorption. This is not accounting for reflection, assuming reflection for many of these would be kind of similar. Here's our old standard technical glass. You can see that that cuts off even earlier, or excuse me, that has an even lower wavelength cutoff, so the transmission on that is actually very, very good. This difference practically doesn't matter too much for solar just because of where the energy is coming in on the spectrum. But this black line here is the Corning Willow glass, and here you see you just get exceptional transparency and optical properties. It goes up, we've taken it up to about 620 degrees for fairly long periods of time. So it has great thermal tolerance. It maintains its high resistant or high transmission no matter what you do to it. And the other thing that's important is it's very resistive because it doesn't have those mobile ions in it. It has a very high dielectric breakdown strength, okay? Which means if you have a big string of modules and you put them together, they're usually wired up in a way where you're going to end up with a very high voltage on the end of that string. And this is actually one of the things that limits module glass thicknesses and weights, is that you've got to have a thick enough piece of glass to make sure you don't shock the guy who's dumb enough to touch the module on the end. You have to have a product that's safe. And so here we can actually meet that with a 100 micron thick piece instead of a 3.2 millimeter piece of glass. Actually pretty cool. It's also hermetic. We've done every water transport measurement we know of. We have thrown at this stuff, and we can't measure anything coming through it. It's great. So we have a lot of tools at our disposal for making CdTe devices. We do a standard CdTe and Cad chloride, very similar to the process done here. We'll probably do it a little bit hotter because of our substrates. But we have a lot of different options for the transparent contacts on the front. We have several different material libraries that we use from, and then we use a bunch of different metallizations or semiconductor contacts on the back. And we can change these out pretty readily from a variety of different systems. Here I'm going to talk about swapping out a chemical bath, a solution-grown Cad sulfide, for a sputter, similar to Jason Kemphart's work here. And then I'll also talk about a back contact tweak that we did to improve things. These are all done on 1.5" square pieces of glass. And we kind of swap things out just to see what works. And this was a slide I made a while ago when everybody said this glass would break. If you cycled it like this, you can't handle it. We've made hundreds of devices. You can break them if you put a probe on them too hard, or if you do something really dumb. We joke that the higher your rank in our organization, the faster you will break a piece of glass. So an associate lab director will break it in under 30 seconds. We haven't given it to a director yet. That'll probably be spontaneous. So we looked at, the first barrier we had is, to look at these contact materials here. There's a lot of work that goes into making these flexible because they're used in the display industry and everybody wants a flexible display. And the urban legend around them is that transparent conducting oxides are inherently brittle and that you cannot bend them. So we started this project, we wanted to first make sure we could make good TCOs on Willow, because if we can't make a cadmium telluride device, we may as well just stop. And then could we bend them, because these things could be deal breakers. So the first question we had is, can we meet this very basic metric for a transparent contact for a CdTe cell, of a resistance below a 15 ohm per square threshold, and transmission above 85 for a lot of it? And the answer is yes. We met that with a variety of different materials. We did it with tin oxide, which is the standard contact in CdTe, Indian tin oxide, which is a standard display material. We use this even though we don't use it in CdTe, because this is the thing that is the gold standard for TCOs and is determined to be brittle. And then cadmium stannate, which is an oddball contact, but we use it in CdTe because it's full of cadmium, and we always like having more cadmium. It also happens to be the best performing TCO known to humankind. So we were able to meet our optical and electrical metrics. We did some XRD to see if there was a difference in the films on rigid glass from the films on flexible